Welcome back. We dip our toe into Chapter 6 today with just a little bit in 6.1, velocity and net change. I like this section because it's a nice application of our fundamental theorem of calculus. So we'll talk about four fundamental ideas: position, velocity, displacement, and distance. Position and velocity we've seen a lot of in this class already. Position is often thought of as a function s of t. Given a time, I have a position. And we often think about this as position along a line at time t. So there is a line, there's a number line, and some object travels. Here I have a little animation. Maybe it moves to the right for a little while, then it moves to the left for a bit, moves to the right again, and continues moving right. So at various values of t, it has various positions on the number line. So maybe at t equals 0, it really starts off at position 0. And maybe by the time 10 seconds elapses, say t equals 10, it's made its way up to 6. And then maybe t equals 15. After 15 seconds, it's come back to a position 2. And then at some later point, t equals 20, it's starting to move right. So for example, I can say that s of 10 equals 6, and s of 15 equals 2. Now, of course, it has a certain velocity throughout this time, and I can compute velocity as the derivative of position. The displacement of an object from time A to time B is simply s of B minus s of A, its position at time B minus its position at time A. So looking at this example above, the displacement of the object from time 10 to 15 will be 2 minus 6 equals negative 4. So it's moved in the negative direction 4 units over that period of time. Now, here's where the application to the fundamental theorem of calculus comes in, because look at this. This is displacement, s of b minus s of a, and s is an antiderivative of velocity. So often we're actually in the situation where I'm given velocity, but I don't know my position function. So this is telling me that even if I just know velocity, I can still compute displacement. I take the definite integral of velocity between 2 points, and that will tell me the displacement between those 2 moments in time. To compute distance, it's a little bit more complicated. What I actually do is I integrate the absolute value of velocity. In the earlier case, with displacement, sometimes velocity can be positive, sometimes it can be negative, and positive and negative velocities sort of cancel each other out. But in the distance case, I want to keep counting distance. I want to keep counting motion. So I can solve that problem by making my velocities always positive, by taking the absolute value. All right, let's do an example. So we'll start with a displacement computation. Suppose that the velocity of an object is given by this function, and that's what's graphed to the right. Notice that at time 0, it starts off with positive velocity. It's moving forward, moving forward. At time 1, it stops. From time 1 to time 3, it's moving backwards. It's moving in the negative direction. At time 3, it stops, and now it starts moving in the forward direction. A little bit like that example I had on the previous slide. It moves forward, it moves backwards, it moves forward again. Let's find the displacement of the object from time 0 to time 3. All right, so that's given by our formula, the integral from 0 to 3 of v of t dt. So that's my s of 3 minus s of 0. And I plug that in. We'll anti-differentiate and evaluate this guy from 0 to 3. Now, when I plug in 3, it turns out that the answer is 9 minus 18 plus 9. And when I plug in 0, I get 0 minus 0 plus 0. And this whole thing is 0. Oh, so the displacement is actually 0. It has moved exactly the same amount forward as it has moved backward over this period of time. All right, let's turn our attention to distance. Let's find the distance of this object over that same period of time. So I will evaluate the integral from 0 to 3 of the absolute value of v of t. Now here's the cool trick. I'm going to split this up. When you have to integrate absolute values, here's what you need to do. split up your interval into sections where the function is positive and sections where the function is negative. So I'm going to split this up into the integral from 0 to 1, absolute value v of t dt, plus the integral from 1 to 3, absolute value v of t dt. And here's why we do that. Because now, over this first interval from 0 to 1, well, the function is positive already. I don't need the absolute values. I can just drop them and it becomes the integral of v of t. Now what's going to happen on the integral from 1 to 3? Now my velocity is negative, and I'm taking the absolute value of a negative velocity, which means it's positive, so I actually end up with negative v of t. V of t itself is negative, so negating that is going to give me a positive value. Now, if I'm adding a negative function, I can simply, I'll do some erasing here. Let's just make that into a big subtraction. So I add the parts where my velocity is positive, and I subtract the parts where my velocity is negative, and that will ensure that the answer I get is always positive. All right, I'm skipping some of the calculation details, but it turns out that this first integral evaluates to 4/3, and this second integral evaluates to a negative 4/3, and so my answer is 8/3. That's the total distance that this object travels over the time period from 0 to 3. All right, last idea, future position. Given the velocity function, how do we actually find a formula for the position function? Can I recover position from velocity? In order to figure out my s of t, I need my starting position plus the displacement from time 0 to time t. So symbolically, that becomes s of t equals s of 0 plus the integral from 0 to t of my velocity. Now notice that I'm using t as an upper limit, which means that I can't use t inside my integral. So you just have to use something else. It doesn't really matter. X is a good choice, so why not? Let's see an example. In fact, let's just continue the example from before. Suppose that v of t is t squared minus 4t plus 3 like we had. Let's find a formula for s of t. Now, I do need to make an assumption. I do need to know something about an initial value, assuming that s of 0 equals 10. All right, so in this case, I can say my formula for t is going to be 10, that's where it starts, plus however much it changes from 0 to t. And so I'll need to plug in my velocity function. So x squared, because I'm replacing my t's with x's, 4x plus 3 dt. And that becomes 10 plus, now I'll anti-differentiate, 1/3 x cubed minus 2x squared plus 3x, and that's evaluated from 0 to t. And look what will happen when I evaluate at 0 and t. When I put in t, my x's just simply get replaced with t's. And when I plug in 0, everything goes to 0. So I end up with 10 plus 1/3 t cubed minus 2t squared plus 3t as my solution for future position. And that's it. There we go. We found our formula, given the assumption that I start off at 10. All right, so take these ideas, give those homework problems a try, and let me know if you have questions. Good luck.